हेलो तामिद। हेलो चेक। ओके। अभी से ऑन करके रखा है क्या? ओके। मैं वो कर दिया ओपन। ओके। मैं वो कर दिया ओपन कर दिया ओपन टू ऑल एंड आई एम गिविंग यू दी ओपन टू ऑल एंड आई एम गिविंग यू दी होस्ट एक्सेस को एक्सेस को डन। चेक कर ले एक बार। डन। चेक कर ले एक बार। अभी के लिए इसको म्यूट में रखो। होपफुली अभी कोई आवाज नहीं जा रहा है यूट्यूब में, बट स्ट्रीम जब स्टार्ट हो जाएगा मैं पॉज से हटा दूंगा। हाँ। हाँ, मैं आपको दे रहा हूँ। हाँ हाँ। हाँ, और लाइक मीट का लिंक शेयर कर दीजिए। लाइक वहाँ पे पोस्टर में स्कैनर लगा हुआ है। लाइक मुझे लगता नहीं कि मोस्ट ऑफ द लोग स्कैन करते होंगे, तो एक बार डायरेक्ट अगर लिंक भेज देंगे तो बेटर होगा। मैं आपको शेयर कर दिया हूँ। भैया एमएल क्लब वाले अकाउंट में भी बोल दीजिए। मैं सोच रहा हूँ कि इस बार वैसे मैं तो करूंगा क्वेश्चन, बट साथ में लाइक कुछ सेकंड ईयर्स भी अगर करे तो बढ़िया रहेगा। लिखिए देख लेना।
the last second here, but should be ready on time here. Just a second. Should be ready on time here. Just a second.
So I was my laptop also. So I was my laptop also has connection problem. So I am afraid. So I am afraid to do that. So I have to do that. So I have reached it, and I am now from the mobile itself. Reached it, and I am now from the mobile itself.
Yeah, we saw the same way all over the world, I guess.
Yeah.
Victims of our technology. So let's see. Yeah, I'm okay now. I think things are ready. I need to probably I can start anytime. I can start anytime.
Okay. So we will start with a brief. Okay. So we will start with a brief introduction, sir, and then I will be handing over the session to you.
Okay. Thank you. Okay. Thank you.
So good evening, everyone. Good evening, everyone. I'm done. I'm Dr. 𝐂𝐻𝐫 Mukherjee. I am sir in NIT Silchar. Dr. 𝐂𝐻𝐫 Mukherjee. I am sir in NIT Silchar. So this NIT Silchar is as presently in so it is presently in so it is present in Silchar and present in Silchar and we are in Assam, we are in Assam, small northeastern state of India, and we are from IEEE Robotics and Automation Society. It's a student branch chapter. And previously, some days back, we received a mail from IEEE Robotics and Automation Society that we can call with distinguished professors for their expert talk on this. And we are very glad to have joined Professor Stephen Lavelle with us today. He has joined to deliver his expert lecture. And so I will be a very short introduction to our distinguished professor. Professor Lavelle has been Professor of Computer Science and Engineering in Robotics and Virtual Reality at the University of Oulu, Finland since 2018. His research interests include robotics, virtual reality, sensor fusion, path planning algorithms, computational geometry, and control theory. In research, he mostly known for his introduction of the rapidly exploring random tree, RIP, and which is widely used in robotics and other engineering fields. He also authored the books in robotics and other engineering fields, and he also authored the books Planning Algorithms, Sensing and Filtering, and Virtual Reality. With regard to industry, he has an early founder and chief scientist of the Oculus VR, acquired by Facebook for $3 billion in 2014, where he developed the patented tracking technology for consumer virtual reality, and also led a team of perceptual psychologists to provide principled approaches to virtual reality system calibration, health and safety, and the design of comfortable user experiences. So I am very glad, I have also, me and my several students have followed his book today, and we are very glad to have you with us, sir, today. And we have been eagerly waiting to hear your talk on this. RRT algorithm, path planning algorithm, and how we can talk on this RRT algorithm, path planning algorithm, and how we can again work on this. What are the new directions in this field? So thank you,
Okay.
and over to you, sir.
Okay, thank you very much. Thanks for the kind introduction. I'm very happy to be here. And if you're all afraid to show your faces, I guess that's okay. But hello, everybody. So you're welcome to switch on your cameras and say hi if you like. It's nice to see people. But I appreciate very much being here today. I wish I could come all the way there and see you guys.
Join us, but seeing the present situation and maybe within this short time, it was means difficult to arrange this. But if you are interested, then surely we will arrange the next time offline meet.
Yeah, maybe sometime. That could be good. I've been to India a few times. Most of my time I'm in Chennai. I have a affiliation position with IIT Madras, so I've been down there a lot. But I've never been over to so that could be very interesting.
It's in the northeast part, sir.
What language do you mainly?
Assamese is the official regional language, but yeah, and Ohomia and several others, as India is a very huge place, so many people talk in many different languages: Bengali, English, Hindi.
Yeah, naturally. I know it's quite a language soup in India, right? All over the place.
Yeah, we all, whenever we are crossing a state border, it feels like a national border because everything, the whole of the scenario changes with language, food, climate, everything changes.
That's why it's funny. No matter how much I go to India, I still feel like I've hardly seen anything. There's so much more that remains, so diverse and interesting.
Yeah.
Let's see. Do you see my screen right now?
I think.
Yes, sir. It's visible.
Okay, so I can do this, and I can maybe do that. Does that seem okay?
Yes, sir.
Okay, very good. So I'll go ahead and get started then. So my generator here for this group, and this is a simple relation that you have. So these relations FB equals the empty string and BF equals the empty string, equals the empty string and BF equals the empty string. These end up being very based way of looking at things. You would need an infinite amount of data. So they say that a picture is worth 1,000 words. This is like some data. So they say that a picture is worth 1,000 words. This is like saying a relation is worth an infinite amount of data. So the amount is worth an infinite amount of data. So the amount of compression here is incredible. It's just some very simple rule, but it doesn't get learned directly. Incredible. It's just some very simple rule, but it doesn't get learned directly kind of from the data. Like a deep neural net won't find exactly this structure. And now like a deep neural net won't find exactly this structure. And now you can extend this. You can extend this to 2D. And you can have a robot that goes moving around to 2D. And you can have a robot that goes moving around with left and right now in addition to forwards and backwards. Left and right now in addition to forwards and backwards. And then you end up with the same kind of ideas, except now you have more relations here. You have like the same ones like we had before, but you also have that going forward and right is the same as going right and forward. So you end up with another relation. This ends up being what's called Z cross Z in terms of basic algebra. So learning these relations would take an infinite amount of data, and they're very, very compact. So there's some value to knowing these things a priori or being able to guess what they are very quickly. Now, once we put obstacles in, then there's some places where you go out of bounds, or maybe I go forward and then forward. If I command to go forward, I have to say what happens. Either I remove the forward action, it doesn't exist anymore, or if you're commanded to go forward, maybe nothing happens if the wall's in the way. If you can't actually go forward, if you move up one place and then you command to go forward, maybe you simply say, okay, that action does not apply. It gets skipped. Does the robot know that it was skipped? That's another question. So what I want to know is for these kind of things, there's still a nice partition of U that should remain. Like what sequences of actions end up being equivalent somehow? We can certainly try to say under what conditions would the robot end up in the same place regardless of the sequence of actions. We can also try to make the robots more realistic by letting them move along curves. So you have a car-like robot and you have wheels rolling, so you can only move in a direction that the wheels are rolling, so you can't move it sideways. There's a lot of things we could add to this, and we made some very general kind of formulations. This is a robot running on a rough surface. So I'll give you another example. So we're not necessarily staying on grid. And then, hang on just a second, someone's at my door. I'm sorry. So that works. Hey, I'm in the middle of a presentation now, sorry. Okay, sorry about that. Thought it might be an emergency, but no, it's all fine. So let's see. So now looking along these general lines, and based on that simple one-dimensional example that I gave you, we've developed at the University of Oulu a very general kind of theory of robotics, I would say. So like something really fundamental. I said robotics is homeless before, very interdisciplinary. So what would the core of robotics look like? In computer science, the core looks like Turing machines and theory of computation, and then algorithms built upon that. And then in control theory, which is also related to robotics, it looks like a theory of parameterized nonlinear differential equations, or linear differential equations in some cases. So we have control systems, and people view it as an application of that. But I think the theory of robotics, we draw inspiration from both of those fields, control theory and theory of computation, but this is something very fundamental. So that's unique to robotics. There are several papers, and these are several people from my research group who developed these things, and it also goes back and